Good morning, everybody. Welcome back to Machine Organization and Programming. This is Monday's lecture. It's actually Tuesday morning. I'm just re-recording the intro here before I release this onto YouTube. I just wanted to put in some more up-to-date announcements. So sorry this video was delayed until Tuesday morning. Yesterday just had a lot of behind-the-scenes stuff going on. Questions on the midterm happened all day long. A bunch of meetings, TA selection for the fall, and the little guy was here playing video games in the background the entire time. I just didn't quite get the editing done last night before it got really late. And I wanted to add just one more announcement to this beginning, so just re-recording this. All right, check it out. We're on lecture 17. If you're thinking you missed one, lecture 16 was the midterm. You did not. Everybody took the midterm at this point. So I'm going to be releasing the exam statistics and the answers later today. Tomorrow at the latest, depends on how long it takes me to go through and just look at the common questions that people got wrong and make sure that they're still fair now that I see what the answers are. Maybe some more of that after I release the statistics as people come back with more questions about the answers and have reasoned arguments about the reason they did things. All right, enough on the exam right now. P3 was released yesterday. It's due 1 week from today. Today is Tuesday at 11:59 p.m. Okay. And the main reason I wanted to re-record this intro is I was going through thinking about how the lecture is connecting to what's going on in the book. I want you guys to listen to the lecture first, watch the lecture, do what I'm doing as far as the guided learning opportunity that I provide, and then go back and read the book. So this is designed to be an introduction to get you guys at a place where the book makes sense. The book is pretty dense. There's a lot of information packed in there, and what I'm trying to do is an overview that gives you guys the flavor so that when you read the book, you're like, yeah, this is familiar. Ooh, there's more information here. The book does go deeper than what I'm doing, and the book has an excellent series of practice questions. I definitely want everybody to go through and you should be able to get to the point where you can do all of the practice problems in the book. Those are going to be great practice for what's coming up on our final exam. Yeah, and throughout today's lecture, I'm highlighting where in the book things are coming from. So hopefully that will be useful so you can see just the connection here. All right, so we're going to begin with a quick review of what we talked about in the last couple of days as far as assembly goes. And then today we're going to, and tomorrow, we're going to start looking at control flow and conditionals. So by the end of today's lecture, we'll get to the basics of control flow. So this is going to be if statements, for loops, and while loops. And to get there, we need to talk about Boolean logic and conditionals. So all right, let's begin with a little bit of review. All right, so just a quick review of some things that are going on in assembly. I'm start back with my picture of what happens when we compile a program. So begin with source code over there on the left side with our sum.c file. This is getting translated by the compiler during the compiler proper stage into sum.s. That is our assembly language version. And then every single one of those assembly statements gets converted directly into a binary code, machine code that the CPU can actually use. So in general, assembly language is mostly human readable, but it's difficult to read. We're not actually going to be doing that much programming in assembly, but what we're going to use it for is to take a look at what our C code is generating so we can think about making the C code more efficient and just understand that connection between what we write in code and how the hardware actually gets to it. So this actually lets us see what's going on even at the register level. And if we take a look at what's going on at the register level, we have a series of 6 general purpose registers. The first 4 are lettered A, B, C, and D. That's the middle letter here in their name. The E stands for extended because we've added an extra 16 bits at the beginning of this. All registers are prefixed with the % to just indicate that currently I'm talking about a register in assembly language. And this is broken into basically 4 parts. I can access the lower 8 lower 8 bits, 1 byte, with the %A, the name of the register, and then the L for the lower, or the next higher 8 bytes with the H prefix. This entire block, the lower 16 bytes, the X here just represents H and L combined. So we can get all 16 of those bits using this addressing. And then the entire extended thing where I've added the extra 16 high order bits is the EAX, E for extended. All right, if we take a look at the set of basic registers, there's a couple more I'm going to talk about in a second, but the A, B, C, and D registers are the ones I can break into low and high and access at the byte level for these bottom half of this. I've got two more here that are also considered general purpose registers. ESI is the source index register, and EDI is the destination index register. In the beginning versions of assembly, these would have been used for very specific purposes, but now we can think of them more as general purpose registers. The only difference is we can't access the lower and high individual bytes in these guys. And then for a control flow with function calls, we have a stack pointer and a frame pointer. We'll be coming in a lot more detail with that tomorrow's lecture. And we have a number of special purpose registers that I'm going to talk a little bit about for just a second. They're not listed in this picture. The very most important one is going to be the instruction pointer, that is the EIP, also known as the program counter. This is going to hold the address of the next instruction to be executed. Now, instructions may vary in size. For all of the examples I'm going to do, I'm just going to assume that the instructions are 4 bytes long, and we'll be reading 4 bytes at a time, but that's not necessarily true. If assembly can get away using a smaller instruction, then it does so. We also have a couple of registers for floating point computations that are not listed here. And there's going to be a hidden register, a special flags register that just provides feedback on what happened with every computation. It's also known as the condition code register or flags register. All right, you may remember last time that we started talking about move instructions and how to access memory. This is all found in our textbook in section 3.4. So what you should do is think about what I did in lecture as an introduction to prepare you guys to dive into the textbook. And I'm going to expect that you will have read the textbook. As we come back later and start using these advanced features, I'll mention them. But definitely take a look at the textbook. Make sure you can do the practice problems. Okay, so we started off talking about, hold on a second. Yeah, we started off talking about how to access memory, how to get data into those registers, and that was the move command. In all of the examples, I'm going to be using the AT&T syntax of IA32 or x86 version of it. And the basic command here was move, but with the AT&T version, I need to add the length of the data that I'm moving. So L stands for long. That's going to be our 4-byte version. W here would be word, which is really misnamed for modern computers. The language was sort of set into assembly a while ago when we were using 2-byte or 16-bit computers, where W just sort of got fixed in the language as 16 bits. B stands for byte, where we're moving 1 byte at a time into like the AH register, for example. Please remember that this move actually is copying data from one location to another. The source isn't changed, so it's more like a copy instruction, even though it's named move. All right, and I neglected one little thing. There's lots of different things that we can move and some that don't work. We can move an immediate value into a register or an immediate value into memory. Those would be like just literal numbers, like a number 4. You can stick that in a register. I can also move the contents of any register to any other register, and I can store stuff in memory from a register, so source and destination, and I can move things source's memory into a register. So all of these work. And then let me click some things that don't work. I cannot move things into an immediate value. The destined can't just be the number 4. That will not work. And the other thing I can't do is move something from a memory location into another memory location directly using this move command. To do this, I've got to do it in 2 steps. I need to move to a register and then back to a different memory location. Now, just a little bit on the syntax of accessing memory. I've got some examples here. If I just put in an address, this can be a decimal address or it can be hexadecimal. The $sign is the one that gave me the immediate value, so I've got to prefix it with a $sign to make it immediate. Otherwise, it's an address in memory. where I'm accessing the memory and storing stuff there or retrieving stuff from it. The other way that I had to access memory was using the parenthesis notation with registers. So when I have a register name, like for example %EAX, then when I put that in parentheses, that means go to memory and use that instead. And then here I've got just one version here. This is going to say shift from this base address value by 8 bytes and grab that address instead. All right, and in general, the most general form of this is the version that has, so I still have parentheses, so I'm going to be accessing things from a register, just an immediate value offset plus the base register plus an index register times a scale factor. So immediate, base register, index register, and scaling factor. So just a quick review about how that move instruction works. Definitely go back, check out 3.4, read that, study it in detail. Let me see here. All right, so let me collapse this down. Here's a great example of something I didn't talk about, the LEA instruction. That's load effective address. Go check it out in the book. It's basically equivalent to the address of operator in C. The ampersand works pretty much the same way, where I can take an address, a source, put it in memory, but instead of actually accessing the contents, it's going to actually grab the address of something and put it into memory. All right, next we talked about the arithmetic instructions. This was section 3.5 of the book, so very much go back, read that, make sure you can do the practice problems. But just a little note on the syntax here in the AT&T version for things like add, subtract, and integer multiplication. We do need to add that suffix indicating the size, and the version is going to have this sort of structure where I've got an add source and destination. And just for subtraction here, it's going to take source and subtract the destination from it, and then store that value in the destination. Okay. Integer division was a little tricky, so just a quick review as we do an example today with this, just to remind you, it's going to be in the PowerPoint slides. So the dividend, that's the numerator, if we're thinking about it in fraction terms, is going to be stored across 2 registers, so we get 64 full bits. The high order bits are going to go in EDX, the low order bits in EAX. If you're doing division and you don't have a giant number, make sure you clear out the EDX register with zeros. Otherwise, you're going to be left over with whatever was in there in the past. And then after our division, the remainder is going to be stored in those high order bits, EDX register, and the quotient will be stored in the EAX register. And then another example of some stuff I skipped over, increment and decrement. These are very simple. It's just increment. Give it the name of a register, and it'll just do the add instruction, but load the immediate value 1 as the source. Same deal with decrement. We'll be subtracting 1 as the source. And then we also talked about the bitwise operators. So the bitwise operators, if we think about and or, these are both binary operators. They're going to operate bitwise. So they'll take the B0 bit in both operands, the source and the destination, and compare them directly. If they're both 1s, in this case it'll store a 1. If either one of them are a 0, it'll store a 0 in that position. The or operator does the same, except it's using or. I do need that suffix, the LB or W. The not and shifting are, well, the not is a unary operator strictly, in that it's just going to take the 1's complement or flip all of the bits. 0s turn into 1s, 1s turn into 0s, and just stores it back in the same position. And then we had 4 different kinds of shifting operators. There were 2 left shifts, the arithmetic and the logical. Both of those did the same thing. They just shift in 0s. Names are there for to give you options, historical, backward compatibility. And if you actually read disassembled code, it's going to sort of just choose one arbitrarily. It's hard to know what they're what's going on, because they do generate the exact same machine instruction. And then for the right shifting, we had 2 versions there. We had the arithmetic and the logical. Remember, the logical is the one that's going to shift in 0s and is used for unsigned numbers when we're doing that sort of transformation. Easy way to remember that is logical has an O in it, LO. It's the second letter, and that's going to shift in 0s. Arithmetic doesn't have an O in it, so it'll be shifting in the sign bit or the high order bit. that's going to be the one that we'll use for signed numbers. And this is technically a binary operator. We need to put in that k value to indicate how many bits we're going to be shifting by. All right, so next we're going to start diving into the new content for today's lecture. After you watch this video, go study section 3.6. We're looking at control flow. And personally, I found this material to be very complicated the first time I went through it. That was a long time ago, and I still think it's quite complicated. So what I'm really hoping to do with this section of the lecture is make the book easy to understand, particularly your first time through reading that book. I really enjoy this part. This is probably one of my favorite parts of the course. It's really just a fun puzzle to figure out how to go from C code into what's really going on at the assembly level, to that deep dive down, because the assembly doesn't give us a lot of the cool features that we have in a regular C program at higher level language. And part of what makes this really difficult to see and figure out the first time through is there's a hidden step with that condition code register that we'll see in a little more detail in just a little bit. So a quick review. Here's what we're trying to do when I'm talking about control flow. So the normal mode of program execution is sequential. We're going to take each statement. So if you think back to like your first week of the most beginning programming class you ever took, we learned that programs operate sequentially. They'll take a look at statement 1. They're going to execute this statement exactly once, and then they're going to move on to instruction 2. Statement 2. It's going to execute this statement exactly once, and then it's going to move on to statement 3. In the normal mode, it's not going to do things more than once. It's not going to skip any steps. It's not going to jump around. It does them in order. Okay, so what normally happens after we execute a statement, then the instruction pointer increments to point at the next statement. The CPU is going to go do the fetch, the decode, and execute, and just repeat. It's just going to continuously go and do this process. But we've got some really cool things we need to be able to do for in higher level programming languages. The next one, it would be conditional statements. For example, the if statement. All right, if you think about this, then like my very first programming class, just back up what's the most basic thing we're looking at. We're going to break that sequential mindset. So here we go. We'll execute statement 1. We get to an if, a conditional of some kind, that says either I want to do these based on some sort of condition, or I don't want to do them if the condition is false, and I'm going to skip over. So what we'll see is we either have one of two different pathways that we'll be looking at the program executing in. So we're going to see one of two things happen. Either we're going to execute all of these statements, 1, 2, 3, 4, just like that in order, or we're going to skip some statements. So a conditional is a way to skip statements. So here we go straight from 1, jump down to statement 4. All right, we can make this a little more complicated with the inclusion of an else clause. In this case, we'll get to this condition, and either it's going to execute these statements, or if it's false, it's going to execute these statements. And then it'll continue on sequentially when we're done. So again, we're looking at one of two different pathways. If the statement or the expression is true, then we're going to be going from statement 1, 2, 3, and then skipping these guys and end up with 6, 1, 2, 3, 6. Or if that expression is false, we'll be skipping 2 and 3, and it's going to go from 1, then 4, 5, and then 6 and onward. All right, so the next kind of control flow we have is iteration. In this case, I've got an example here of a while loop. So we'll begin with statement 1 and everything that came before it. We'll get to this condition right here, and then we're going to execute this block of statements 0 or more times up to, no limit. And then when we're done, when the expression evaluates to false, we'll move on and execute statement 4 and the rest of the program. So if we look at this, when I think about what's going on with these statements, I've got a number of options, things that could potentially happen depending on that expression. I could go from statement 1, skip the loop entirely, and go straight to statement 4 and continue onward, depending on what happens in that expression. I could execute the loop exactly once and get 1, 2, 3, and then continue on with 4. Or I could see iteration occurring, and I could go from 1, then 2, 3, and then do the loop again, 2, 3, do the loop again, 2, 3, do it yet again, 2, 3. And it's not just going to happen exactly 4 times. I've got lots and lots of options. I can go through this loop any number of times. And eventually I'll exit the loop and continue on with statement 4. So after the loop ends, I'm just going to go back to my sequential mode of operation and continue on. And then finally, I didn't draw a picture for functions. I think we'll come back to functions. The way this is implemented in assembly is a little more complicated. We need to do a little more work, and this will be in tomorrow's lecture. The basic idea of a function, though, is that I'm going to jump to a new piece of code, execute that piece of code, and then jump back to wherever I came from. I'm going to return. And from many places in the code, I can jump to those same sequence of statements. It's actually really great programming practice to sort of encapsulate different pieces of code so that I don't worry about making mistakes if I have to type them over again. So we'll talk a little bit more in detail coming soon as to how functions are implemented in assembly. So I want to ask the question and just start to think about this. What do we really need at the assembly level to implement these? We don't have a while statement or a for statement or a do while or an if statement or even a function call statement. What we do have, and what we're going to take advantage of at the assembly level to do this, hold on. What do we really need? The things that we've seen in all of these different kinds of the conditional and iteration are Boolean operators or relational operators, things that we use to make a decision about whether we execute these statements or not. Do we execute them again or not? And so we had less than, greater, less than or equal to, all the way up to exactly equal to. But at the assembly level, this is implemented a little differently. We don't just have a less than operator we'll pull out and use. Instead, what we do have is a bunch of registers. All right. Most importantly is this instruction pointer register. So what we're going to need to do to jump over some code is to change this instruction pointer register. So normally this increments after every step. We're going to see that it's going to retrieve the instruction, decode it, and then execute it, and then go get the next one. Well, that instruction needs to be to change the instruction pointer to point to a new instruction so that it skips over some instructions, or so it goes back and repeats them as an iteration. And what we're going to use instead of the Boolean operators we've seen before is the set of flags in the condition code register. So this is just one 32-bit register like the rest of them. And a number of those bits are Boolean flags, true, false, that we'll use to make decisions about whether we jump over some code or jump back and repeat it or jump to a function. That register is called eFlags. The book doesn't actually, I don't remember seeing the flag's name. They talk specifically about individual bits. But the ones that we're going to see are important for what we're doing today are the carry flag, the zero flag, the sign flag, and the overflow flag. So we'll just be looking at 4 of those bits as we make decisions about how to control the flow of execution. Okay, so before I start talking about conditionals, I want to take a deeper look at the condition codes. I'm going to use addition as an example. These flags, they are set every single time we perform an operation. Again, it's a 32-bit register holding flags. We're just going to be looking at a couple of these for the purposes of deciding control flow. The first one I want to take a look at is the zero flag. But the point I want to make is these are updated after every single operation, not just a comparison operation or a relational Boolean kind of operation, everything. So, for example, if I take a look at addition, here's my example. If I'm looking at something like assigning a target the sum of a plus b, in that case, for an example, to take a look at the zero flag, if I'm looking at 3 plus minus 3, that's going to give me a result of 0. And the zero flag is going to say the result of the previous computation, whatever I just finished doing, is going to be set to 1 if that result, the target here, is equal to 0. So if we assign a value of 1 to the zero flag, we're going to say that the flag was set, as far as vocabulary goes. And if it's not equal to 0, then the zero flag will be set to 0, or not set, or unset. I'm going to use these interchangeably. I think not set is the technical way that they talk about it in the book. But my vocabulary, I use unset more often, so that's what I mean when I say unset. It's just set to 0. Now, the book goes into great detail about how we can access individual flags and like extract the value or set the value. I'm going to skip all of that. Yeah, next up, let's talk about under what conditions the carry flag is set. Let me go make another slide for that. All right, next up, I'd like to talk about the carry flag. So this is another one of the condition codes that's set after every operation, not just when I'm testing for a particular Boolean condition. And just a quick note, the carry flag is used for unsigned numbers, even though it's set after every operation. So let's just take a look at an example. So again, I'm looking at addition to begin with. So if I have a plus b, if I'm adding 3 plus 4, in this example, I'm using exactly 3-bit architecture. So I get 3 bits here in binary. 3 is 0, 1, 1, 4 is 1, 0, 0. If I add these together, 1 plus 0 gives me 1. 1 plus 0 gives me 1, and 0 plus 1 gives me 1. There was no carry out required. I didn't do any carrying at all. And I'm not referring to just individual carry within here. What I'm looking at is, did I need a 4th bit to represent the sum? And 3 plus 4 is 7. That worked just fine. So no carry out was required. So this bit will not be set. Okay, if I look at an example that does have carry out, for example, if I'm looking at 3 plus 5, in this case, I've got 0, 1, 1 and 1, 0, 1 for 3 and 5. The first step is to take 1 plus 1. That's equal to 2, and 2 in binary is 1, 0. So I write the 0, I carry the 1. And then 1 plus 1 is 2 again. In binary, that's going to be 1, 0. So I write the 0, I carry the 1. These carries are not going to be responsible for setting that carry flag. It's only this next one. The 1 plus 1 is 1, 0 again. So 0 and 1. The final answer I get when I add 3 plus 5 is going to be this 0, 0, 0. The answer is 0. That 1 is lost. But what it's going to do is just take note that I had to carry out, and I would have required a 4th bit in order to complete this and get the right answer. So the carry flag here is going to be set to 1. This also works for subtraction with unsigned numbers. So just a quick example, if I'm taking 1 and I subtract minus 2, in order to do this computation, first 1 take away 0 is going to be just 1. And then I'm going to take 0 and subtract 1 from it. This is a problem, so I'm going to need to borrow. So I look over to the left, and what the computer is going to do on the inside is borrow from this imaginary 4th bit right here. It's going to assume that that's a 1. Yep, there we go. Assume that's a 1. And then it's going to borrow from that. So it's going to move over here to this next digit and say, borrow the 1, 0. So there's the 1, there's the 0 is actually equal to 2. So I can do that. I can borrow from that. And then I can borrow from this 2 right here, and that'll give me a 1, 2, just like that when I borrow from it. And now I can do my subtraction. So 2 take away 1 is going to be equal to 1, and then 1 take away 0 is going to be equal to 1. But I had to borrow from right there. So this will result also in the carry flag being set when we borrow. So check this out. 1 take away minus 2 is equal to 1, 1, 1 in the computer. That's in unsigned numbers equal to 7. So again, we got this computation wrong because we borrowed in from an imaginary bit that's not actually there. And so this will result in this carry flag being set. All right, next up, the sign flag. This one's actually pretty straightforward. It's used for signed numbers, and it's just going to do some sort of operation. In this case, I'm looking at addition. A plus b, if that target, when I'm done with the computation, is less than 0, the sign flag is set to 1. Otherwise, the sign flag is set to 0. So just a quick example of signed numbers again. So if I'm looking at addition of 3 plus negative 4, this is going to give me minus 1 in the end, so the sign flag will be set. But just here's an example. So 0, 1, 1 is 3. In 2's complement, signed integers, minus 4 is 1, 0, 0. So when I add these numbers together, 1 plus 0 is 1, 1 plus 0 is 1, 0 plus 1 is 1, and 1, 1, 1 is going to be minus 1. So what we see, the sign bit, or the sign flag, is just this most significant bit right here. It just gets copied straight into the sign flag. So if it's a negative number, this will be a 1, and if it's a positive number, it'll be a 0 right there. So pretty straightforward, used for signed numbers. Okay, and the last flag we need to take a look at in order to understand what's going on with the control flow, if looping iteration, is the overflow flag. This is basically the same as the carry flag, except it's the signed number version, where the carry flag was for unsigned numbers. So here's the basic idea. I'm still looking at addition, and remember that these the condition codes are set with every operation. It's just hidden. It happens behind the scenes in the background. They never tell us it's going on. It's just there. So if I'm looking here, let me do some examples. If I'm looking at 2 plus 1, or 0, 1, 0 in binary plus 0, 0, 1, I'm going to get 0, 1, 1. That's no, yep, there it is, 3, 0, 1, 1, no problem, totally works. I get the correct answer. If I'm looking at 3 plus 1 in binary, so 0, 1, 1, I'm going to take the 1 plus 1 is 2, so that's 0, 1, I carry. 1 plus 1 is 2 again, I get the 0 and carry, and I end up with 1, 0, 0. 1, 0, 0 in signed 2's complement number representation is -4. This did not result in the correct answer. We have overflowed. So here the overflow flag is set to 0. When it worked, when I got the wrong answer, the overflow flag is set to 1. Think about it like this. If I draw the number line, these are all the possible numbers I can represent with signed 2's complement in 3 bits. And so what I've done here is I've taken 3, which is the last one, I add 1 to it. It basically wraps around and I get to the -4. So that overflow indicates any time I've wrapped around. So if I were to take something like -3 and add -4 to it, that's going to just count backwards. 1, 2, 3, 4 places. I'm going to go from 2 negative numbers being added together. Should be a negative number as the result, but I see I get a +1 as the answer. So couple of little just observations, I guess. If I take any positive number and any negative number from this number set and I add them together, I must get another number that exists on this set. I can't overflow if I've got one positive and one negative number. Any combination works. Now, where I can see overflow is if I've got 2 positive numbers, they can wrap around and end up on the negative side. Or if I've got 2 negative numbers, I add those together, they can wrap around and end up on the positive side. So for addition, this is going to be set if a is greater than 0, b is greater than 0, and I find that the target result t is less than 0. Oops, I used lowercase t's. Didn't mean to do that. Sorry, guys. I'll fix it for next year. So in this case, the overflow flag will be set to 1. If I have 2 negative numbers, a is less than 0, b is less than 0, and I get a positive result, then overflow flag will also be set. Else, the overflow flag will be set to 0. So those are the 4 condition codes that we're going to need to care about. Next up, I'm going to introduce another instruction, the compare instruction. All right, so next up, I'm going to be introducing 2 new instructions for setting the flags, the condition code register, so that we can use the result of these computations to make decisions about control flow. The first one is the compare instruction. That's CMP, and then it takes the suffix LWB, just like all of the other operations. And this is going to be comparing B and A. So again, this would be source destination. And essentially what it's doing is a subtraction. So A minus B, because we flip those around. And the destination is the one that is, or the source would be the one that gets subtracted from the destination. So this is evaluating A minus B, but it's not going to store the result. It doesn't do anything other than set the condition flags. So what I want to do is just go through and quick review what's going on with these flags for a subtraction problem, specifically for compare. Okay, so first up, if A minus B exactly equals 0, then we're going to set this 0 flag. So this only happens if A is exactly equal to B. So this is the same thing as the equals operator. Okay, next up, the carry flag. If you remember that the carry flag is for unsigned numbers, and this is really only set when we need to borrow during subtraction. So, and that only happens if I subtract a big number from a small number. So if I take 3 and subtract 4 from it, I need to borrow. Anytime it's going to give me a negative answer. So this is really the same thing as saying that if A is smaller than B, and I take B away from A, then that's going to set the carry flag. So this would give us that relational operator. These two flags together are going to give us less than or equal. So I hope you guys can see sort of where the relational operators are coming into the assembly version of things. We're going to be doing sort of math. It's going to set some flags. We're going to look at specific bits, and we'll use those bits to make a decision about whether we jump or not. So in the end, we're going to translate all of these to, less than or equal. All right, so all right. I got getting distracted, Mike. Okay, so the next one, the sign flag. Here we go. Similar to the carry flag, but for sign numbers. And anytime we subtract a big number from a small number, that gives us a negative answer. So a minus b is less than 0. Anytime that happens, we can also write that a is less than b. Okay, so again, this is the relational operator less than for sign numbers in this case. And the overflow flag, we'll come back a little bit in just a little bit about how this is actually used. But this has that complicated formula. For subtraction, the only difference is I had to switch the sign on the b. So if a is positive and b is negative, and the result I get is negative, then the overflow flag is set. We did not get the correct answer. Or if we've got a negative number and I'm subtracting a positive number, and then the result is actually positive, I've overflowed or wrapped around the number line. And so this flag would be set here also. All right, next up, the test instruction. Okay, so the test instruction is just going to compare A and B, but it's going to do the bitwise AND operator, but then not store the result. So syntax is going to be test L, B or W. I need that suffix. B comma A. Doesn't matter which order I put these in, because it's just going to do the binary bitwise AND operator. This is almost always used with the same operands, so it's going to be test L A comma A, and this is going to set just two of the flags, the 0 flag and the sign flag. So if we take a look at the 0 flag, if I do A and B, this will tell me that every single bit is either 0 or they're different. One could be 1, the other could be 0, but they can't both be 1. So this isn't super useful in a lot of cases. However, if I test with the exact same number, so if I've got A and A, if they're both 1, I've got 001 and 001, I will get a 001 as the answer. And so I can use this to say it's not equal to 0. If I do get 0, then I can just go ahead and say A is equal to 0, and the sign flag will be set. So this is a test for is the number 0, if I'm just looking at one number. All right, hope that made sense. The other one I care about is the sign flag. And in this case, if I compare A and B, this is the bitwise AND operator again. If I get an answer that's less than 0, basically this is, we only care about the most significant bit for the sign flag. So just that far leftmost one, the one that represents the sign bit. If they're both equal to 1, as in they're both negative, then this is going to evaluate to 1, and we will set the sign flag. And again, these are almost always used with the same operand. So A and A, if this is a negative number, that sign bit will be a 1 in both cases. The AND operator gives me a 1, and so I can use this to say that A is less than 0. So it's just a quick test for something that's negative. And just a quick summary, some examples to hopefully make this really clear. There's only really 3 options for the test operation. So if I've got a number that's exactly equal to 0, when I compare it to itself, the 0 flag is set, the sign flag is not. All right, pretty straightforward. If it's less than 0, then obviously the 0 flag is not set, it's not 0, and the sign flag will be set because it's negative. For positive numbers, the 0 flag will be not set, of course, it's not 0, and the sign flag will not be set either because it's not negative. All right, so next up, we're going to talk about how these are used to actually control the flow of a program. All right, wow, I'm about 5 hours into my recording process here. It's taken me longer than any other lecture so far. But we finally made it to the jump instructions. These are going to be the ones that let us jump over pieces in a conditional, like an if statement, if it's false, or that let us jump back to the beginning of a loop. So here's the basic idea. I've got a series of instructions, and somewhere in there, I'm going to have a jump instruction. So it'll operate do instruction 1, then it'll jump to the target. What this is going to do, this is an unconditional jump. I haven't checked any conditions. This will just immediately take the instruction pointer and move it down to the target location, actually the instruction after my target label. So I'm going to have labels throughout there. They're all indicated by a colon. A lot of the labels begin with a period for different sections of code. I left that out here. It's more of a convention. And if you actually read the disassembled code, they'll almost always use L1, L2, L3, and it'll be .L1, .L2. So I'm just using target as my own personal label. I can, if I'm writing the assembly code, I can choose anything I want to make it meaningful. But anyway, so this will jump over instructions 2 and 3 and just carry on with instructions 4 and 5. This is essentially a go-to statement right out of C. All right, maybe something a little more useful at this point, if we take a look at an if statement. So the structure of an if statement is going to have some kind of instruction that will set the flag. This is going to be the evaluation of the conditional inside the parentheses of my if statement. And then I'm going to do some kind of test on that to decide if I want to jump. This instruction, the conditional, is always that subtraction problem, b minus or a minus b. It's compare CMP BA, and that'll do a minus b. And then once I've done that computation, I can take a look at all of the flags and choose an appropriate condition for which to jump. So in this case, it's going to jump to my target if the 0 flag is set. So if the result of that computation is 0, so if I'm comparing A and B, that means they have to be exactly equal when I subtract to get 0. So if A is equal to B, then that'll give me 0, and I'm going to jump over this. So essentially, if that condition is false, I go straight to the after the if block and jump to my label. So this would imply an if statement with no else block. I'm just either going to do these instructions. So either I jump if it's 0, or I don't jump if it's not 0, and end up at the target and continue on regardless. Just to finish this out, we have lots of different kinds of jump instructions. So far, my example just used 0. There's also a jump if not 0. And then we have all of the relational operators, less than or equal to, greater than or equal to, and not equal to. For all of this entire set here is, for signed numbers. For unsigned numbers, we have jump if below or equal, jump if above or equal, and then we also have the equal and not equal. So we're going to use above and below when we're talking about unsigned numbers. That's where these abbreviations come from. So if you're looking at different conditional operations, relational operations to decide if I jump, I need to use different instructions depending on whether I'm looking at signed numbers or unsigned numbers. So assembly will keep track of that. All right, and now the whole reason I spent so long talking about the flags is what's going on inside. This is how we can understand what's happening. So these are the requirements before these jump conditions are executed or not. So like I was just saying, I didn't put the 0 one in. Yeah, I jumped 0. Oh, all right. So I've got this is a subset of the flag requirement. So if I'm jumping if they're equal, that's one of my options. There, I'm going to do the subtraction problem, b minus a or a minus b. And if the 0 flag is set, that means they're equal, and I will do the jump. There's also a jump not equal right here. That's just going to check and see if the tilde there is the bitwise not. It's just going to take that one bit, just the 0 flag, take the the complement of that. So if it's a 1, it switches it to 0. And if I get a 1 there, then it'll take that jump. For less than, that's going to just take the sign flag and make sure that we didn't have any overflow. Or if we do have overflow, that means we've also got a less than condition. All right. The jump less than or equal, I'm just going to OR with the 0 flag, just because it could be equal. Greater than is the less than, but I've complemented it. So I'll take the condition for less than and just invert it, and that'll be greater than. Same deal with less, that's greater than. Oh, timeout, let me fix that. All right, got it fixed. Greater than or equal to, I'm going to complement the condition for less than. And then, or it could be 0. For the unsigned integer comparisons, if it's below, I just need to look for the carry flag. Below or equal to, that's the carry flag or the 0 flag. For above, then I didn't have any carry, so make sure the carry flag is set to false. And remember that subtraction problem, anytime I take a small number and subtract a bigger number from it, I needed to borrow in. So that's what this is doing. If it's below, if I needed to borrow, and that's where the carry flag gets set. All right, and then finally, if the carry flag is to be above, I need to have not set the carry flag, and the 0 flag cannot be set. Okay, pretty straightforward. And then just to get the above or equal to, in this case, it's just not the carry flag. All right, at this point, I've got a worksheet. Go download the worksheet, pull that up, and we're going to take a look at some of those problems. All right, so go ahead and start with problem 6 on the worksheet. This is just going to ask us to take a very simple if statement and turn this into assembly. So pause the video, go give this a try, actually write something down, commit to it, and then come back for the solution. And solution in 3, 2, 1, click. Click. Okay, there we go. So if we're looking at sort of a structure to do a simple if statement, one with just the if block and no else block, basically I need to evaluate a condition, and then I'm either going to do the if statement or not. So I'm going to jump here. So an if statement is always a condition and a jump. Those two statements gets broken down into those things. And then I'm either going to have like a do block or a don't block for an if true or else. So in this case, what this is going to look like is what I need to do is first make sure I set all of those, the condition codes. So I'm going to do a comparison here. Compare, L stands for the long. Tell me the data type. I'm comparing contents of register B to register A, or EBX. And this is going to be reversed again from what I would see up here. And this is going to do the subtraction. It's going to take EAX, subtract B from it, and then set all of those flags. So if all of these flags are set, if A is greater than B, then I need to do, what I'm really doing is I want to jump to the end if this is not true. If it's true, I can just go ahead and do the block. So if A is greater than B, then I want to do the block. I want to jump when this is not true. So what I really want is the jump if less than or equal to. And then I'm going to jump down to my don't block and skip all of the code. So if this is not true, then I want to do what's in this block right here. So I need to increment A. So that's just going to add 1. I wanted to do it this way with the immediate value 1 added to EAX. So that's going to take EX, add this, and store it back in EAX. So essentially the plus plus operator there in one step. All right, cool. So now, oh yeah, and because I'm never actually using my do label right here, I just put it in sort of as like a scaffolding, some structure. I can take that out at the end. So I'll do my comparison. I'll jump if I don't want to do the log. Otherwise, I'll do what's in the if statement right there, and then carry on with statements beyond the don't. Okay, now go ahead and take a look at worksheet problem 7. We're going to do basically the same thing. This is now an if else block. So if A is greater than B, we're going to do that code, else we'll do that code. So go, now that you've seen how problem 6 is done, I sort of laid out step-by-step like thought process, the scaffolding. Pause the video, see if you can work through that. Actually commit, write it down, and then check your work. All right, answer in 3, 2, 1, click. Okay, again, I've got my scaffolding here. An if statement is always going to have this condition and a jump, those pair of statements. I need to set some flags, and then I'll jump depending on whether they're true or not. So I've got an if true statement, an if block right here. If it's true, we do that. So that'll be my do block here in assembly. Else, I want to do this stuff. So that'll be the don't block. And then at the end, I need to be able to jump over the else block here. So I've got another label, the end. Okay, so what this is going to look like, I'm going to compare the two registers again. This is the same comparison. If it's true, then I want to do this block. If it's not true, then this will be the reverse of this. It'll be less than or equal. If that's not true, then I want to jump down to the else block and do this one instead. So the less than or equal. All right, so if that's false, then I'm going to do this block. I'm going to just increment EAX by adding 1 again, and then I need to jump over the else block. So this is an unconditional jump. No condition is checked. It just automatically jumps to the end over here and skips over the else block. It executes this block, the move. So this is the assignment operator. I'm assigning A to B. So my source is A, destination is B. I'm just moving this data into a new register. This is making a copy. It doesn't actually change EAX. Sorry about that. Forgot to turn off my phone. And then, this block is executed if this is less than or equal. So if this is false. All right. Hopefully that's clear. And again, I never actually used the do label right here. So I can go ahead and eliminate that to keep my code a little cleaner. I think as far as scaffolding goes, it makes sense to put it in. There's nothing wrong with having extra labels that are never used. It makes code a little more clear if you've got like an if statement. All right, so next up, go ahead and take a look at worksheet problem number 8. We're looking at a while loop right here. See if you can use what you've learned so far in lecture and write some assembly code that'll take a look at this loop, and then pause the video, come back for the answer in 3, 2, 1. All right, guys, so I'm back with the answer. So if I'm looking at the structure of a while loop, and again, I've got my scaffolding here. So we're going to have a condition, and whoops, what did I do? All right, sorry, I clicked on the screen and it jumped ahead. So I've got my condition and then a jump statement. That's always going to be what we see for like an if statement or a while statement. Those pair of statements go together. And then I'm going to have my statements, whatever's here. And then when I get to the bottom of this, the bottom of while loop right here, I need to go back and evaluate this condition and decide if I'm going to do this again. So I've got an unconditional jump up to before the condition. So I've got my top label right here. If the condition turned out to be false, then I don't want to execute any of these statements, and I certainly don't want to just jump back up and have an infinite loop. So I'm going to instead jump to the bottom of the loop. All right, let's take a look at what these statements really look like. If I'm comparing B to 0, I just need to know if it's positive. I'm going to do the test instruction instead and compare B to itself. That's going to set 2 flags. It's going to set the 0 flag and the sign flag. And the operation that compares the 0 flag and the sign flag is the jump less than or equal. And if that's true, then I want to skip the loop. So B is greater than 0. I want less than or equal to jump to the bottom. Okay. And then just for variety and to demonstrate some other things, for the increment, I've got an increment. These take all of the suffixes too, so L for the long data, incrementing A, and then decrementing B. And again, then jump to my top label and got my bottom label if I want to skip this loop. All right, so that's going to wrap it up for this lecture. I'll be back tomorrow with more examples of this and functions. So have a great day, everybody, and good luck on the midterm.